Okay, so here I am back in the garage, and it turns out all this sitting around on my chair, it wasn't good for the back. I threw my back out a little bit, but it's feeling a lot better. I've been getting good advice from the elderly. Well, I shouldn't say just the elderly, but Oma's hooked me up. She loaned me her heating pad. That's helping. And I took a hot bath, and I'm doing all right. But because of that, I'm going to use a new type of technique to do the lecture. I'm using paper and pencil and pens, and instead of standing up at the whiteboard. At the whiteboard, actually, I ran out of that whiteboard spray, so I got to go back to school tomorrow and get more spray. So that wasn't going to work that way either ways. But it's all right. We're gonna get through this together. All right. See you in a second. Okay. Before we start with chapter 16, I do want to do one last thing from chapter 15. Remember, in chapter 15 we learned how to sulfonate a benzene ring with the fuming sulfuric acid. And this made benzene sulfonic acid. And I did say this one was special because it can be reversed. So let's do that. So if you take the benzene sulfonic acid and you add dilute sulfuric acid, so you add water. Adding water helps drive this reaction this way, and you need to heat it up. This one needs some heat. You can get your benzene back and your SO3 gas, which will bubble away. So let's look at the mechanism for this. The mechanism will be the reverse. You'll start off in dilute sulfuric acid, your sulfonic acid will actually be deprotonated because its pKa is about -3. So that's a pretty strong acid, so water will come along and deprotonate that. So I'll make it colorful for us. Okay, here we go. I swung the pi bonds around on the benzene ring. It doesn't matter. Okay, so that's what we have in our dilute sulfuric acid. And here is where things get a little bit crazy, and you do need heat for this. That's why we have the heat. But we're going to actually, we're going to put the hinge here. We're going to protonate the benzene ring in this manner. And it's going to lose aromaticity again. Hydronium's doesn't seem like it would be a strong enough acid for this, but I guess with heat, it works. And we do need to get a hydrogen back onto that carbon. All right, so there's that, there's that. I got my carbocation right here, and I made water. All right, now I need to get rid of this guy. And oh, I'd have resonance for that. You can practice drawing out that resonance. And so how am I gonna get rid of this? I forget. I need to, oh yeah, sorry. It's gonna drop down the lone pair from the oxygen. And then it's a push-pull. The oxygen's pushing the electrons that way, and the carbocation's pulling electrons that way. And there we have it. Re-aromatized. We put a hydrogen back in place of where the sulfonic acid was, and we regenerated the sulfur trioxide gas. And that's it. This reaction could actually work. It's usually done with dilute sulfuric acid, but if you just use steam and you heat it up, hot water, you can do it too. We're going to see this is going to be very useful because we're going to use it in chapter 16. This sulfonic acid is a blocking group, we call it, but it's sort of like a protecting group. You'll see that coming up soon. All right, chapter 16, here we are. So in chapter 16, we're looking at electrophilic aromatic substitution still, but now we're going to focus on the Regio Chemistry and the kinetics. How fast the reactions go, and the faster reactions make the major products. So what kind of reactions are these? Kinetic control reactions. So outcome 1 talks about resonance and induction. We're going to use these concepts to explain a lot of this chapter. So first off, let's review what they are. Resonance, remember, is electron flow through pi bonding. And resonance can go a long distance in a molecule, actually. And you see a lot of resonance, right, in aromatic rings. And then induction is electron flow through sigma bonds and space. So remember, let's see how the color looks on my phone here. Looks okay. I think I should better colors though. So remember when we talk about how you have an atom that's very electron withdrawn, then very electronegative. It can pull electrons to it through sigma bonds in space. That's induction. Let's look at a couple acid-base examples first. Some review. I think you should probably all know this right off the bat. Let's compare the pKa of ethanol to acetic acid to trifluoral acetic acid. So which do you think is the strongest acid? Hopefully you put TFA as the strongest acid. This is trifluoral acetic acid. It's a common one called TFA. And its pKa is 0. Nice, huh? Right at 0. And then we already know the pKa of acetic acid. It's like 4.74, 4.75-ish. And then ethanol, it's about 15, 16, right? So trifluoroacetic acid is the strongest acid. Why is that? Well, by induction, the fluorines can pull electrons through the sigma bond to them because they're very electronegative. So can this oxygen. And through space, the oxygen can pull electrons. So if the oxygen and the fluorine are pulling electrons away from this OH bond, they're making that OH bond weaker because it's the electrons that hold the hydrogen and the oxygen together. So these electronegative atoms are inductively withdrawing electrons, making this more acidic. Now the same can be said over here, but it doesn't have fluorines, it has hydrogens. So it's got the electronegative oxygen here, but not the fluorines. So you can see it's not quite as strong of an acid. It's still withdrawing electrons from that bond, but not as much. And then for the alcohol, these are sp3 carbons, are electron donating. So there's not getting that inductive electron withdrawing to make that as strong of an acid. So that was the view of looking at the acids before they react. That's one way you can look at it. So you can look for acids you can look before reaction. And then you can also look at the conjugate base. All stuff we've done before. This is just a good review. So to do that, I can add water and then have that be our base to deprotonate these. This is something you've seen over and over, right? It's not very favorable here, you should know. There we go. No resonance for this. It's a pretty strong base. And then if I add water to this one, same thing happens with the acetic acid, but in this case, I will have resonance in the conjugate base. Whoops. And what is that going to do? That's going to stabilize the conjugate base, make it less reactive and a weaker base. So the resonance is helping spread out that negative charge so it's not concentrated on one atom like this, and that makes it more stable. And its resonance is electron flow through pi bonding. Next up, I'll just abbreviate this one. I'll add water and the trifluoral acetic acid becomes trifluoral acetate. There we go. And you'll have the hydronium as well. Okay, and this has resonance like the normal acetic acid. All right, so it's got the negative charge spread out by resonance, just like acetate. So its resonance is helping stabilize the base, but it also has this fluorine that's withdrawing that that negative charge towards it because it's so electronegative. And it does that through sigma bonds and space. So this base is stabilized by induction from the fluorines and by resonance. This only has resonance stabilization, and that doesn't have resonance or the inductive stabilization. So we'll say this is our strongest base. And this is our weakest base. See if that's on camera. Yeah, it's on camera, good. And so weakest base has the strongest conjugate acid. Strongest base, weakest conjugate acid. All right, let's apply this to aromatic molecules. Outcome 2 has some phenols and their pKa's. I'll start off with just regular old phenol. So what would you guess the pKa of phenol is? Probably 15, 16, right? Turns out its pKa is actually, we're going to be super precise, 9.95. I usually think of it as like about 10. It's a lot more acidic than a normal alcohol. That's why we actually don't even refer to it as just, and a lot of people will say it's like an alcohol, but it's got its own name. It's a phenol. Because it's on a phenyl ring. Okay, so let's check this out. Why would that be? Let's think about it before it reacts. Before it reacts, you could say, oh, this carbon here, it's sp2 hybridized. Is that going to make a difference compared to like ethanol? Ethanol is attached to an sp3 hybridized carbon. Ah, there's something there, huh? So remember our electronegativity trend that we're going to work with is sp3 carbons are the least electronegative in this series, then a hydrogen, then an sp2 carbon. So an sp2 carbon is more electronegative than the sp3 carbon. So that means it can withdraw electrons from that OH bond via induction more so than an sp3 carbon, which would more so like donate, so the induction would make this a stronger acid because that bond is not going to be as strong. It's not going to have as much electron density. And now, so that's looking at it before it reacts. Let's look at it after it reacts. Use water. We're using water as our base because we usually refer to our pKa's in an aqueous solvent. So water then would be the base. Okay. We could talk about this in terms of the O- at negative charge is an area of instability. An sp2 carbon is going to stabilize the negative charge more so than an sp3 carbon would, because with the ethanol we saw when we got the minus charge, the sp3 carbon would actually say, oh, you have a negative charge oxygen, here's more, donate a bunch. Where the sp2 carbon is trying to withdraw. Now, oxygen's more electronegative than sp2 carbon. I don't know about when oxygen's negative though, but this is more electronegative than that. That's key. So that's going to help stabilize the negative charge. But what else, even more important than that? I've got a lone pair, a single bond, a double bond. Lone pair, single bond, double bond. Oh, it's got resonance. So this can resonate into the ring. Now that resonance is going to help. It's not as great a resonance as you might think because what happened, well, no, I think it's fine. Never mind. Let's keep going. It's got more resonance. It can put the negative charge on the ortho position, and then it can go down here. I was running out of room to the para. I got a negative charge on the para position, and it can also resonate to the other ortho. Like so. So the negative charge is spread over the oxygen, orthocarbon, paracarbon, and the other orthocarbon. So this conjugate base is stabilized by sp2 carbon induction and 1, 2, 3, 4 resonance structures. And we can draw the resonance hybrid. All the way around the ring. Most of the negative charge is going to be on the oxygen, but there'll be some negative charge on the ortho, para, and meta positions too. And so that makes phenols pretty acidic. You can, in a lab setting, you can deprotonate phenols with just basic sodium hydroxide water, whereas normal alcohols aren't deprotonated that well. So you can, by just using like basic sodium hydroxide water, you can make a phenol negatively charged, and then that would make it more water soluble instead of organic soluble during extraction. Okay, so we got phenol. So let's look at some other ones. Before I move on, I forgot to put in the intro that Megan made a pretty sweet mechanism video. It's in our student videos. DE videos. And it's along with the mods. Hers is it's an internal alkyne synthesis. A mod's got alkyne synthesis up there. So check those out. She got extra credit for that. You should make your own mechanism or retro or whatever has helped me learn. Send me the video and I'll share it with the rest of the class. All right, now back to this acidity thing. So we looked at phenol. Let's look at, next up, para-nitrobenzene. Oh, I'm sorry, para-nitrophenol. Let's see what happens here. Okay, it turns out the nitro group is one of the strongest electron withdrawing groups. I used to joke and say it's like the Hoover of electron withdrawing, because Hoover was the common vacuum back in the day. But now I'll say it's like the Dyson ball vacuum of electrons. So it really sucks electrons to it. And it sucks electrons through it through induction and resonance. So what do you think that's going to do to the acidity of this phenol? Do you think it's going to be more acidic than regular phenol, less acidic, or the same? I'll give you the answer. The pKa for this one is 7.14. So it's much more acidic. It's about 10 to the 3 orders, like 3 orders of magnitude. So that's about 1,000 times stronger acid than regular phenol. And that's because the nitrogen is more electronegative than the hydrogen that we had initially. So we're comparing hydrogen right now with the nitro group. Nitrogen's more electronegative than hydrogen, and it's got a plus charge, making it even more electronegative. So it's pulling electrons to it through the sigma bonds in space. And we're gonna see resonance will play a part too. Let's go ahead and deprotonate it and look at the conjugate base. Before I say that, I wanna make sure you get this idea. So the electrons here between oxygen and hydrogen, they're like the glue holding this oxygen and this hydrogen. The withdrawing of those electrons are like removing glue. So this bond becomes weak, more reactive, a stronger acid. Makes it easier to be broken by, say, a water molecule. And when you're drawing your nitros, remember the nitrogen's always positive. Formal charge, let's not forget that guy. That plus charge there, I like to see it because it emphasizes that that thing really wants to pull electrons towards it. Let's see if my video is all on. Looks like I'm on track here. Okay, now this conjugate base, we're gonna see it stabilized by resonance as well as induction. So this lone pair could drop down. There we go, and it went over to the ortho position again, and now it drops again, and it's going to go here to the para position again. All right. And then it can continue over to the, this is para, right? It can continue over to the other ortho. See if I can squeeze this guy in over on the page over here. I think I can. There we go. And is that all the resonance for that one? This had 1, 2, 3, 4. 1, 2, 3, 4. Is that all it's got? Nope. There's another one. This guy is stabilized by a whole nother resonance structure. And it occurs with, I'll use a different color pen. That was kind of a gray. I don't know what color I'll use. Blue? Is blue gonna stand out? I'm gonna try the green again, why not? So this lone pair can also resonate down into here like this. So I'll make this green too to emphasize it's coming from. I don't know if that helps you or not. But here's what we get. There's a double bond there to the nitrogen. Still a positive charge. And now each oxygen has a negative. That looks pretty ugly. Can you tell? I'll zoom it in. Oh, does that help? Are we looking at it? Are we looking at it? Where'd it go? Right there. Can you see the double bond to the nitrogen? Okay, good. All right, so this acid is a stronger acid because look at that. It can, after it's deprotonated, its conjugate base is stabilized by a very electron withdrawing group through induction and through resonance. All right, let's try another one. All right, let's look at meta-nitrophenol. So before we look at the para-nitro, now we put it over here in the meta position. Will that change anything? Well, the nitro is still a very strong electron withdrawing group. And the pKa of this one turns out to be 8.35. So not quite as strong of an acid as the para. Let's see, what was the para again? Regular phenol was 9.95. The para is 7.14. And now our nitrophenol, 8.3, not as strong of an acid. It's actually closer to the phenol, so you think the induction might be better? I'm not sure what's going on. Well, I am, but let's imagine I'm not sure what's going on, like you might not. Let's actually go ahead and just deprotonate it, start looking at the conjugate base. And as I'm drawing these out, you might have a tendency to just watch me. You're much better off if you're pausing and trying to draw them out yourself. I should be saying that all along, like I have before, but I'll say it now. If you're not pausing the video and drawing these out on your own, you're not getting as much out of this. Okay, here we go. All right. So now let's look for resonance for this guy. I can drop the lone pair down, and again, it goes ortho. Is anybody getting tired of drawing the nitro? All of its formal charges? It's okay, it's worth it, we're learning. All right, so we go to the ortho position. And then let's go ahead and look at the next resonance. Oh, wait a minute, look at that. When the nitro's methyl, the lone pair just passes it up. So I have a pi bond here, a lone pair there. There it is. Will I be able to get a pi bond to the nitrogen? Doesn't look like it, huh? Let me look back at the para one. On the para one, we had the negative charge on the oxygen, goes to the ortho, goes to the para, and then the para can go to the other ortho, but it can also resonate down into the nitrogen. Our meta one's gonna miss that resonance structure, huh? Because from the oxygen, the lone pair can only go ortho and para and then next meta. When the nitro's in the meta position, it doesn't get to resonate in with that. I can even like abbreviate it, call it NO2, poor guy. Doesn't get to play in this one. Our curved arrows are like this. Yeah, so it looks like when the nitro is meta, it results in a conjugate base that's not as stabilized. It doesn't get that extra resonance. It only has 1, 2, 3, 4 resonance structures to stabilize its negative charge. Whereas in the para case, it got 1, 2, 3, 4, and a 5th resonance structure. So the para's conjugate base is more stable. Weaker base, stronger acid, pKa 7.14. Stronger base, weaker acid, pKa 8.35. Pretty cool, huh? The position of the nitro will affect its reactivity a lot. We're going to see the same thing with electrophilic aromatic substitutions. All right, let's summarize where we're at so far and add a new one in there. So we got the para-nitrophenol, that one is pKa 7.14. Let me write this better. pKa over here, 7.14. Then the pKa of the meta-nitrophenol, 8.35. Not quite as acidic because the conjugate base can't get help from the nitro via resonance, but it does get help via induction, the withdrawal of electrons through sigma bonds. Then the phenol, kind of the standard here, its pKa is 10.20. It's got one hydrogen here that we're comparing, well, and there's a hydrogen there too. So when I was comparing these two, I was comparing nitro to hydrogen. When I was comparing these two, I was comparing that nitrogen to this hydrogen, right? All right, so when I come to this one, I got a methoxy group on here. Wonder how that's going to affect it. Oxygen is actually a pretty electron withdrawing group, right? It's pretty, through induction, it's pretty electronegative. We would say usually, pretty much everybody says fluorine's the most electronegative, oxygen's next, and then chlorine. Some actually switch these two, but it's still one of the most electronegative atoms on Earth. So how do you think that's going to affect the pKa? Is it going to be more acidic than a phenol? Oh, you know what? This is 9.95, sorry. Hopefully you were not freaking out. That's 9.95. This is 10.20. It turns out the methoxy makes this a weaker acid than phenol. Not by a lot, but it does make it a weaker acid. That sounds like crazy talk. You're telling me hydrogen, which is not very electronegative, is going to make a stronger acid out of this phenol than an oxygen? Crazy, huh? Let's consider that oxygen on there. So it's an interesting thing. Those of you who have already done the extra credit are probably like, oh no, I'm fine with this. The England extra credit, because last year I was in England during spring break and a couple days after. So anyways, let's talk about this. The oxygen, we got to consider it in terms of its induction and its resonance. So in terms of induction, is it more electronegative than a hydrogen? Yes. It is more electronegative than hydrogen, so that means in terms of induction, it's electron withdrawing. And if it's electron withdrawing, that means it's making this bond weaker and it's making it more acidic. All right, what about resonance? Does it seem like it's withdrawing out of the ring with resonance? We saw that with the nitro group when it was para. The nitro group we saw can resonate out of the ring, right? If I put a hinge here, boom, boom. Just like that, right? Electron withdrawing by resonance. Yeah, the nitro withdraws through resonance. But what about this oxygen? Can it take a pi bond to it? if I hinge here, I have the hinge there, and I pull it, that'd break the octet rule. So oxygen is actually not electron withdrawing through resonance. It's electron donating through resonance. It goes like this. Now, is that major resonance? No, not major. But it's still part of the nature of this molecule. And when it donates electrons in, it's giving the ring more negative charge, more electrons. And so those electrons are some of it's being given into this OH bond, which makes it stronger, makes it a weaker acid. So it's interesting. The induction for this, electron withdrawing, the resonance, electron donating. What do we have to say then overall? Since one is saying I'm a withdrawing group, one's saying I'm a donating group, we have to go with our experimental data. The experimental data says that this phenol is a weaker acid than the regular phenol. So that means it must be overall an electron donating group. Pretty interesting, huh? Oxygen's an electron donating group. It is overall, and we're going to see this in terms of its reactivity as affecting acids, affecting bases, affecting nucleophiles in electrophilic aromatic substitution, and affecting carbonyls as electrophiles. We're going to see this a lot. It's kind of weird, huh? Oxygen's an electron donating group when it can resonate in. So let's talk about, remember we talked about that pi bonding too. So when this oxygen and carbon pi bond, the carbon has a 2p orbital, and the oxygen has a 2p orbital. And we mentioned that, oh yeah, the 2p to 2p can be strong pi bonding. There we go. Strong pi bonding. So sorry for my sloppiness on this one. That's a nitro group. So pKa of that one, 7.14. I don't expect you to memorize these pKa's, but I would like you to be able to say, oh, that's more acidic than that, or even all. I'd like to be able to rank all these. Well, it'd be tough to rank this one versus those two, but I definitely, well, you'll see. So 8.35 for that one. It's a little less acidic when it's meta because it can't resonate into it. Now this one I'll leave blank. The phenol is 9.95, and the methoxybenzene when it's para here is 10.20. And now I've got a parachloral group there, and I'll just give it away. That one is 9.14. So interesting. We saw that the oxygen could withdraw through induction because it's electronegative, donate through resonance, and the resonance won out. That 2p resonance won out. So this was overall an electron donor to the ring, making the acid weaker, lower pK, higher pK. Now what about this? If it's got a lower, if the parachloral has a lower pKa than just phenol, that's kind of crazy. We're comparing it to the H. Well, actually it's not so crazy. This one sort of makes sense. So you'd think, oh, chlorine's pretty electronegative. It should withdraw from the OH and make it a stronger acid, and it does. So overall, this is an electron withdrawer, the chlorine. And the hydrogen is our reference. Okay, so what is the nitro group? Electron withdrawer. It's more acidic than that. And the paranitro is even a stronger electron withdrawer. Okay. So we got that. Let's talk about the chlorine. Why is that guy an overall withdrawer where the oxygen, which is so similar with its lone pair right there, overall electron donor? So let's consider this one. In terms of the chlorine's induction and its resonance, and then overall. Well, we already know the answer for overall. It is electron withdrawing. We have to base that on experimental data. You can experimentally measure that pKa. So induction. Is chlorine more electronegative than hydrogen? Yep, a lot more. So relative to hydrogen, it's an electron withdrawer. Now what about resonance? Can it resonate out? Can a pi bond come out and double bond to the chlorine? It's kind of, yeah, I guess it can, because it doesn't have to obey the octet rule. But that's crazy talk. This is actually going to be, it donates into the ring by resonance, like so. Okay, so there we go. And when it does this, it is a minor resonance structure because you got a separation of charge here, but it's still part of the character of the molecule. And this is now negative charge being put in the ring, making that bond a little stronger, huh? So that's electron donating through resonance. But which one wins out? The induction withdrawing or the resonance donating? Looks like induction wins this time. For the oxygen, it was the other way. For the oxygen, it was electron withdrawing through induction. It was the same. Here, I'll just write it here. So this is for chlorine. This is for oxygen. Electron withdrawing through induction. Electron donating through resonance. And overall, it's electron donating. So they're similar in induction, but something must be going on here. Let's take a closer look at the chlorine's resonance. Let's look at this pi bond. So the pi bond there is between a big chlorine atom and a little carbon. So I've got the carbon's 2p, and then the chlorine's got these weird extra nodes, and it's much bigger. It's using its 3p orbital. So is this resonance as good? No, weak resonance. Not like the 2p resonance of oxygen. So that's the key. The resonance donation for chlorine is weak, so the induction wins out. It's an overall electron withdrawer. I like that stuff. I hope you like it too. And to understand it, you just got to practice it. A nice thing to recognize with this stuff is that if you have a benzene ring that has some atom X with a lone pair attached to it, in terms of resonance, it'll be electron donating like that. If you have, instead of an atom attached with a lone pair, an atom that has a double bond to another atom, that's going to withdraw through induction. Through resonance. Electron withdrawing. So, for instance, electron donors would be things like we've already seen. You had the methoxybenzene, right? You saw the chlorine. And things like bromine would fall in this category. An amide would fall into this category. This amide might be a little tricky because it's got a pi bond there, but remember the pi bond has to be first atom off of the ring, and that's further down the line. So for all of these, you can see resonate into the ring, electron donating. Resonate into the ring, electron donating, into the ring, into the ring. They're all electron donating by resonance. Whereas these ones are electron withdrawing. You just saw the Nitro group was electron withdrawing. Other examples are a ketone. That would be electron withdrawing. Or sulfonic acid. And other examples. All right, so for this exam coming up on Wednesday, I said I would just have the acid-base part of chapter 16 in there, and I'm holding true to that. So expect on exam 2 something like this. Maybe I'll give you bromobenzene, benzene, and oh, I'm sorry, parabromobenzene, phenol, and say paraminophenol. I can ask, rank these in terms of their acid strengths and explain your answers with resonance and induction. So I'll go ahead and just answer this one for you. So I'm going to say the bromine is an overall, well, let's just work it out. Let's go induction, resonance, overall. So the bromine by induction, is it more electronegative than our hydrogen on the regular phenol? It's more electronegative. So the bromine is going to be electron withdrawing. Okay, how about hydrogen? That's our reference. We'll call that like, it's like a 0 point. We're saying this is electron withdrawing relative to hydrogen. Now the nitrogen, is it more electronegative than hydrogen? Yes, so it's electron withdrawing as well. Next up, resonance. Does the bromine resonate out or into the ring? It resonates into the ring. So that's electron donating. The hydrogen, that's our reference, and it doesn't resonate into the ring. The amine resonates into the ring. They're both looking the same, but overall, I want you to be able to predict this, that this will be electron withdrawing overall. And how would you know that? It's going to follow the same pattern we saw before. The carbon to bromine pi bond is not very strong because this is a 2p, and the bromine's got like extra nodes, and it's much bigger. So it's because it's a 4p orbital. This is much weaker bonding, weaker pi bonding. So this electron donation due to resonance is weak, and the electron withdrawing wins out. And then on this side, the pi bond is actually quite strong between the carbon and the nitrogen because they both use the 2p atomic orbitals. So donation's going to win out, and it's going to be electron donating overall. And so what's the strongest acid in this group? The withdrawing overall. Strongest acid, and then the overall electron donor is the weakest acid. I may not even ask it as what's the strongest, weakest. I don't know. I might just give you the pKs and ask you to describe these. Yeah, that's probably the way I'll do it. This way you don't have to rely so much on knowing for sure like this kind of stuff. But all right, that should be easy points for you guys. You know it's coming. All right, we were looking at the phenols and their acidity. And you saw that when you have a phenol, which is an acid, if it has an electron donor attached to it, that makes it a weaker acid. And if it had an electron withdrawer That made it a stronger acid. And what do you think? If you're comparing, if we're talking about acids and bases, how do you think they match up with electrophiles and nucleophiles? What do you think's more like an acid? Well, I should start with base. What do you think's more like a base? An electrophile or a nucleophile? Hopefully you say nucleophile, because they're both negatively charged. They have extra electrons. They want to reach out and make bonds. Where the acids are like electrophiles, because they have the positive charged hydrogen, and things come and they accept pairs of electrons. Okay, so with that in mind, let's get back to electrophilic aromatic substitution. So remember, in electrophilic aromatic substitution, if you have the reaction, you react, your benzene is your nucleophile, and then you have to make a super electrophile, and you get a substitution reaction with putting on your super electrophile, substituting it for the hydrogen that was there. Okay, so if I have an electron donating group to this nucleophile, how will that affect it? Do you think it'll make it a stronger nucleophile or a weaker nucleophile? Electron donating groups made the acids weaker, but remember, acids don't really correspond with nucleophiles. An electron withdrawing group is going to make the nucleophile more negatively charged and thus a stronger nucleophile. And instead of just saying, oh, it makes it stronger, for some reason in electrophilic aromatic substitution, everybody tends to think, instead of just saying stronger, they say it activates the ring. So an electron donating group to a benzene ring makes the benzene ring activated. Makes it more reactive, it'll react faster. And then would the opposite be true? If you have if your benzene ring's your nucleophile, reacting with the super electrophile, and you're making your product, if I have an electron withdrawing group, what is that electron withdrawing group doing? It's taking electrons out of the ring, and that makes the ring less negative, thus a weaker nucleophile, and we say the ring is deactivated. Following that activated thing. Oh, let's see. Yep, it's all on screen. Let's look at some examples. If I start with just benzene and I want to do a nitration, I'd add nitric acid, sulfuric acid, and I get my nitro group on here. And O2, right? Okay. Let's say I'll set that relative rate to 1. I'll say that's my standard. Just like benzene was phenol was the standard for the acid talk. Benzene itself is the standard here. And now let's say I add to this guy a methoxy group like that. What's gonna happen when I add the nitric acid? Well, this is what's going to happen. I'm going to get my major product as the para product. And I'll talk about the Regio Chem, why it's para shortly. But before I do that, let's just look at the relative rate. Do you think this is going to react faster than benzene? So I'm comparing a hydrogen to benzene. I mean, a hydrogen to methoxy. The methoxy, in terms of induction, it's electron withdrawing because oxygen is more electronegative than hydrogen. So that pull of electrons through sigma bonds in space. And then in terms of resonance, it's going to donate in, right? Because it's got that lone pair. So it's electron donating. And what wins? Oh yeah, the oxygen's got a 2p orbital. Carbon's got a 2p orbital. The resonance is going to be strong. So overall, it's going to be electron donating. So if this oxygen's donating electrons into the ring, making the ring more negative, is that making it a stronger nucleophile? It is. So this reaction is going to be faster than benzene. And how much faster? I think it's like maybe 10,000 times faster. It's pretty interesting, huh? Just adding that group on there. So this guy, this group is an activator. Okay, next up, nitration, of a chlorobenzene. So let's try to predict this one. Oh, I'm showing you the major product, the para, and I'll talk about why it's para later. Right now, I just want to know how fast is it. So the chlorine, by induction, it is electron withdrawing. We know that because chlorine is more electronegative than a hydrogen. And by resonance, it's what? Electron donating. And we know that because it's got a lone pair that can donate in. Overall, what should it be? Overall, it'll be electron withdrawing. Why is that? That's because the pi bonding for the resonance is through the carbon 2p and the chlorine's 3p. Doesn't match up well. It's weak resonance. So the resonance doesn't help that much, the donation. The withdrawing through induction is the main thing. So if this chlorine is overall taking electrons out of the ring, making it less negative, is it going to be as good a nucleophile? Nope. So will this react as fast as benzene? Nope. Its relative rate is about 0.033. So it's like 300ths of times as fast as benzene. We say that the chlorine is not an activator, it's a deactivator. Deactivates the ring, it reacts slower. Next up, let's look at and see how this ester would affect things. This ethyl ester. So the ethyl ester is going to give us actually the meta product is major. Again, I'll tell you that later. I'll talk about why that is later. But let's look at whether or not we think this ethyl ester is an activator or a deactivator. It's induction. Let's consider that. We're comparing now an sp2 carbon to the hydrogen. Is that still on screen? But it's okay. To the hydrogen of benzene. So an sp2 carbon is more electronegative and it's got these oxygens. So it's electron withdrawing in terms of induction. In terms of resonance, it's got the pi bond right out there. Is there a lone pair here? No. This is going to withdraw through resonance as well. So it's also electron withdrawing through resonance. So this is easy to determine the overall effect. So overall, electron withdrawing, it's got to be electron withdrawing. So the ester is withdrawing electrons from the ring, causing it to be less negative, not as nucleophilic, a weaker nucleophile, slower to react, and it's a deactivator. So this reacts slower. How much slower? 0.0037, even slower than the chlorine. The chlorine had some donation through resonance that can take away some of the withdrawing through induction, but the ester, it's withdrawing, reacts very slow. Okay, so what we've seen so far is that if you have an electrophilic aromatic substitution reaction and you have an overall electron donor attached to the benzene ring nucleophile, it activates it. It makes it react faster. If you have an overall electron withdrawing group attached to the benzene nucleophile, deactivates it. Let's look at a specific example here. I have a phenol and Br2 and iron 3 bromide. And I know earlier I talked to you about the acidity of phenol, but now we're not looking at the acidity of phenol. We're looking at this phenol as a nucleophile in an electrophilic aromatic substitution. A lot of times my students get mixed up at this point, but I don't want you to. This has a certain reactivity as an acid, deprotonating that, and that's one type of reaction we studied. But we're also going to look at this molecule and see how it reacts as a nucleophile in electrophilic aromatic substitution, a different reaction. And its reactivity here is a nucleophile, which is opposite of an acid. So is it going to be an activator or a deactivator? Let's work it out. So in terms of induction, it's electron withdrawing. The oxygen is more electronegative than hydrogen. In terms of a resonance, it's electron donating because it can donate its lone pair in. Overall, it's electron donating because the resonance is strong. It's between a 2p oxygen and a 2p carbon. So this guy is an activator. And that's the kinetics part of it, the rate. It reacts faster than benzene. Now, finally, we're going to do the Regio Chem of this. So when the phenol reacts, it could put a bromine ortho or meta or para. Okay, what does it produce most? Well, it actually produces mostly the para. This is our most major product. The meta is our minor product. So you'll get very little meta. Sorry, I had drawn a bond there, so I just added the H because maybe I'll just scratch it out. But it's a hydrogen. Okay, so that's our minor. This is our second most major, the ortho. Okay, so let me put some numbers on this. So I'd expect maybe like, I don't know, 5% of the meta product and maybe 65% para, 70, maybe 30% ortho. So a fair amount of ortho still, mostly para and just a little meta. It turns out we call this guy an ortho-para directing activator. That's what we call the alcohol, because it directs products mainly to ortho and para, and it's an activator. It reacts faster than normal benzene. This reacts about 1,000 times faster. Let's look at another one. Before I explain why it's ortho-para, let's try a different one. Let's look at sulfonation of nitrobenzene. I know we've learned how to put nitros on a benzene ring, but now once they're on, how are they going to direct the next thing to be added to the ring, and how will they speed up the reaction or slow it down? Let's look at that first. Let's see if a nitro group should be activating or deactivating. So in terms of induction, is the nitrogen atom and the two oxygens, are they more electronegative than hydrogen? Yes. So they are electron withdrawing. In terms of resonance, let's look at it a little more carefully. I'll draw out the nitro group. Here we have it. In terms of resonance, oh, I almost forgot the plus charge on the nitrogen. The hinging here, pi bonds can swing up out of the ring like that. So it's electron withdrawing according to resonance. And I did say earlier that nitro groups are one of the strongest electron withdrawing groups. So it should make sense that it's both withdrawing through induction and resonance. So overall, it's very electron withdrawing, meaning it's what? An activator or a deactivator? Deactivator. Because as you pull electrons out of the ring, you make it less nucleophilic and less reactive as a nucleophile. All right, now let's look at these yields here. That's the kinetics. Now let's look at the Regio Chemistry. You know what we're going to get most of? We're going to get like 95% of the meta product. Very little of the other stuff. Let's say maybe 3% para and maybe 2%, maybe even less ortho. So this one's different, huh? The last example we had an ortho para director. This guy is a meta directing deactivator. The nitro group. Interesting, huh? The last example we saw, we got a ortho para directing activator. Let's try one more and then I'll explain the ortho para directing and the meta directing. Okay, let's look at acetophenone here. It's a ketone on a benzene ring. When you have the methyl ketone on a benzene ring, it's called acetophenone. So let's see about activation and deactivation. So in terms of induction, sp2 carbon, more electronegative than hydrogen. So this is electron withdrawing. Resonance, it's going to be electron withdrawing as well, because it doesn't have a lone pair there. No lone pair here. Pi bond there, yep. So overall, easy. It's electron withdrawing, meaning that it is a deactivator. So let's look at the yields. The last deactivator was meta-directing. I wonder if that happens again here. And it does. It could be like, I don't know, 98% this one, maybe 1% para, 1% ortho. So yes, this is a strongly meta-directing deactivator. The ketone is that. This table is a nice example of helping you predict ortho-para directors, meta-directors, activators, and deactivators. So if you look at this, if you have a benzene ring and you're at a super electrophile, dun, 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 in the X position, if it's an NH2, so imagine you have the bond to the nitrogen, this lone pair, it's two hydrogens, it's going to be a moderate or strong activator. NH2 will be a strong activator because you can see it can donate into the ring and it's 2p to 2p resonance is going to be strong. So all of these are activators. You notice they've all got lone pairs. And then we're going to see that alkyl, and we won't talk much about that, but if you're curious, phenol, they're weak activators. And then the halogens are actually deactivators. And that's because, well, for the chlorine, bromine, iodide, they have weak resonance. For the fluorine, it's 2p to 2p resonance. That should be strong, but it's the most electronegative element in the world, so that makes it induction win out for it. And then, so these are all ortho-para directors. Some are activators, some are deactivators. And then the meta-directors, they all happen to be strong deactivators because they withdraw through induction and resonance. And you'll, if you draw them all out, you'll see a pi bond, that has a pi bond. This one doesn't have a pi bond, but it has a plus charge. It's very electron withdrawing. No pi bond, but yeah, these ones are a little strange, but they're truly there. Pi bond, this has a pi bond coming off of there. And then all. Okay, so if you put these different groups on a benzene ring, see where R is, I put an alcohol. The OH there is actually a phenol. What do I get? How's my reaction rate occur? It occurs fast. It's activated. It's 1,000 times faster than when just an H is here. When an H is here from the R position, that's benzene. Put an OH on there, it reacts 1,000 times faster. It's overall electron donating due to its strong resonance. And it produces mostly ortho and para. It's an ortho-para director. And very little meta. Whereas the methyl is weakly activating. It's because it's sp3 hybridizing. It can electron donate through induction. And it has no resonance, so it's just donating. And it's an ortho-para director. And then hydrogen's your reference. When you put a chlorine on the methyl, that's electron withdrawing. Now, an sp3 carbon with a chlorine on it, I guess overall, is electron withdrawing, no longer donating. That chlorine's so electronegative. The iodide has lone pairs on it, ortho-para directing, but deactivating because its resonance is weak. Chlorine's the same way. This is an ester, deactivating, meta-director. Nitro, meta-director, strongly deactivating. Nitro with a plus charge, strongly deactivating. Interesting stuff. Let's look at the nucleophile before it reacts. Remember when we were looking at acid strength of the phenols at the beginning? We said that we can look at the acid before it reacts and see how strong its OH bond is and whether we think it's going to be a stronger or weaker acid. We can look at the nucleophile before it reacts actually to see, well, we've already been doing this. We've been seeing how if it's activated or deactivated. We can also look to see if it's an ortho-para director or a meta-director for most of them. So let's look at one that we already know. I'll switch it up a little bit. Oh, yeah, I'll just make it ethoxybenzene. So what do you think about ethoxybenzene? Does it look like an ortho-para director or a meta-director? Those are the two type of directors. This is our question. So let's check this out. If I look at resonance, even though it's minor, before it reacts, I'll get the following. I could put that negative charge. I could put a negative charge on the ortho, and then I can resonate another step, and the negative charge is over on the para. It skipped over the meta. And then I'll move it over to the other ortho. So it appears the lone pair and the oxygen can only resonate to the ortho, para, and the other ortho. And so if we make a resonance hybrid of this, it'll look like this. Where it'll have a delta minus on a carbon, ortho, para, ortho, and the oxygen, and I'm going to say mostly on the oxygen since that's major resonance structure. So what does this look like? It's a nucleophile in these reactions. Where does it look most nucleophilic? Does it look more nucleophilic at the ortho or the para? I mean, the ortho or the meta? At the ortho-para. It's an ortho-para director. Isn't that nice? It works out great, huh? And then you tend to get more para, and I like to chalk that up to steric hindrance. The ortho should have an advantage over the para because there's two ortho positions you can react at versus only one para. But you tend to always get more para, so it must be their steric hindrance to here, I guess. Or maybe the induction affects these orthos more. I don't know. But as long as we can predict it, ortho-para directing. And is it an activator or a deactivator? By induction, it's withdrawing. By resonance, it's donating. Resonance is 2p stronger. So this is an ortho-para director, and it's activating because it's going to overall, resonance in is going to beat out the induction out. Okay. Okay, we got an amide for this one. Let's see how it works before it reacts. Let's look at some resonance for this. Got the nitrogen over here with the lone pair, but it's not directly attached to the ring. And the carbon that's directly attached to the ring has no lone pairs. So this is going to be resonates out of the ring. So we put a positive charge on the ortho position. Then that positive charge can move around the ring. And it continues to the para, then over to the other ortho. I know these resonance structures are a little strange, but they're following our rules, and they do affect how this molecule reacts. So it looks like we get a positive charge at the ortho, para, and the other ortho position. So are those positions, the ortho and para, are they being activated? Are they more nucleophilic as when they're positive? Let's look at the resonance hybrid of this. So are they more reactive there? The delta minus on the oxygen, delta plus ortho, and para. So, I think a plus charge seems like not nucleophilic. I think it's going to be less nucleophilic in those spots. And the meta doesn't have to have that positive charge. So I think it's going to be more nucleophilic meta, and that's what it is. This is a meta directing. And is it an activator or deactivator? Through induction, sp3 carbon, withdrawing. Through resonance, withdrawing. So withdrawing, it's a withdrawer overall, it's deactivated. So these are meta-directing deactivators. All right, let's try this ethyl benzene before the reaction. Can we predict if it's an ortho-para director or a meta-director? Well, I can't draw resonance. That would, it doesn't resonate into the ring or out of the ring. So you know what? For these ones, you can't necessarily tell if it's an ortho-para director or a meta director. I can tell you about if it's an activator or a deactivator. In terms of induction, it's an sp3 carbon. Is that sp3 carbon more electronegative or less electronegative than hydrogen? It's less electronegative than hydrogen. So it's actually through induction an electron donor. And we know that sp3 carbons, they're electron donating. They stabilize carbocations and radicals, right? What about resonance? It has no resonance. So overall, this is an electron donor. It's actually a weaker electron donor experimentally, but it's a weakly activating group. It reacts about 25 times faster than benzene. So yep, it is donating into the ring, making it more negative and nucleophilic, so it's going to react faster than benzene, but it's not in the 1,000 times faster like some of the other activators. Okay, but I still don't know about ortho-para directing or meta directing. With the alkyl groups, it's up in the air. I can't figure it out before the reaction. There's another way. Just like we predicted the acid strength before it reacted and then the conjugate base of the acid, we're going to be able to predict these orthopara versus meta-directors before the reaction for most of them, not with alkyl. And we'll be able to also predict it while we look at the aromatic, the one after the aromaticity is lost, the carbocation intermediate. We're going to look at that carbocation intermediate. Okay, I took the ethyl benzene and I reacted it with this acid chloride and the aluminum chloride to make the super electrophile. And so it can produce a ketone ortho, meta, or para. So what do we get mostly? Well, first off, is this an activator or deactivator? Do you remember? It can donate in through induction because it's an sp3 carbon. They're not very electronegative. It has no resonance. So it's an electron donor overall, and it's an activator. But what do we get the most of? Well, you run this reaction in lab, you're going to get mostly this. Maybe like 70% this one, para. Maybe 25% ortho and 5% meta. So looks like experimentally we have this guy being an ortho-para directing activator. It does react faster than benzene. So we can't predict the ortho-para before it reacts, but we can with the intermediate. So the way we're going to do that is to draw the curved arrow mechanism. Let's do it. So the acid chloride has to first react with the aluminum chloride, and the oxygen is more nucleophilic. It can add to the aluminum, but it can come off, come on, come off. Occasionally the chlorine can add, and we will get the Lewis acid, Lewis base adduct like that. And then I like to show this guy coming off, pop, pop, because that's a nice push-pull. That lone pair can push down. And I get my super electrophile. All right, here's where it's going to start coming all together. I have my ethyl benzene. Let's go ahead and put it ortho. When I put the ketone in the ortho position, I create a carbocation there in the meta position. Then that carbocation has resonance. And before I move on to that carbocation, let's talk about this one. What kind of carbocation is that? That's a secondary carbocation. Okay, and then when I resonate it over, oh, you know what? I want to wiggle this. Wiggle, wiggle, wiggle. Wiggle, wiggle, wiggle. That's the stereocenter. So I've got that H there. All right, and now what kind of carbocation do I have for my second resonance structure? Secondary carbocation as well. Nice. Then I got one more resonance structure. When I drop that pi bond around there like a windshield wiper, get this guy. Here we have it. What kind of carbocation is this? Hope I'm not off page, sorry. This is a tertiary carbocation. So looky, looky, we got a secondary component, secondary, and a tertiary. That tertiary one's gonna be the major one, right? That's gonna add a lot of stability to this pretty high energy intermediate. And to finish off the reaction, we'll have our catalyst regenerated. And I know it's crazy to use chloride as a base, but these are crazy times. and a crazy mechanism. I can draw this mechanism from any resonance structure. I'll do it from this one. Why not? And we re-aromatized. And we put that ketone in the para position and remade our chloride. Okay, so that's the ortho. Let's now check out the meta. For the meta addition mechanism, I'm gonna start at the super electrophile. And I'm gonna imagine a hinge here on the metacarbon. That pi bond swings open, makes the bond there. And I lost my aromaticity. And I get that carbocation intermediate. And it has resonance. Oh, before I move away from this one's a secondary carbocation. I swing my pi bond over like that. That one's really looking like a windshield wiper too, huh? Wee, wee, wee. And we get this one. There it is, there it is. Wiggle, wiggle, wiggle. And then that one is a secondary carbocation as well. Then I can swing this pi bond up here. Oh, and looky, looky, I got a secondary carbocation again. So for the meta attack, I got a secondary component to my carbocation, secondary. When we did the ortho addition, we got a secondary, tertiary. So what do you think? Which intermediate is lower in energy? Ortho with its secondary, tertiary, or meta with its secondary, carbocation component. Ortho is going to be lower in energy. So do you think that's the rate determining step to form that carbocation when you lose aromaticity? It is. And that's part of the rate determining step. So isn't that awesome? It's going to be faster to make the ortho over the meta. And that's what we're seeing as our product ratios. We got more ortho and less meta. All right, and then I guess we got to look at the para. Okay, here we go with the para addition. Hinging off the para carbon. Add to our electrophile. Lose aromaticity. And this one's, interestingly enough, not a stereocenter. So I won't wiggle that one. I still got my hydrogen there, right? You know, on the last one, I never finished it, but hopefully you're okay with that. That's going to deprotonate that and go there and give me your final product. Okay, let's look at our resonance for this one. So I start off with what kind of a carbocation? Secondary carbocation. Hinge here. Oh, look at this. Looky, looky. Ortho para director showing its true colors. There it is. We got a tertiary carbocation. The meta didn't have any tertiary carbocations. And I'll finish off the resonance. See what we get next. Hinging here and swing that way, and I got another secondary. So the para has a secondary, tertiary carbocation. So it's similar to the ortho. It's a lower energy intermediate, easier to form, and thus faster to form, and it leads to more product because this is a kinetic controlled reaction. I'll finish this one off for you. So it's just AlCl3. And that's your final product. Let me talk a little bit more in more detail about that. Oh yeah, I got another page here. I'm writing on someone's grading, sorry. I get free notes out of this. I'm running out of paper and whiteboard and sleep. Okay, so I'm gonna show a partial reaction coordinate diagram for this reaction. I'm gonna start off at the ethyl benzene and the superelectrophile. Try adding those if you want. I think the first step's X indo, maybe XO. No, this one's gonna for sure be indo. So I start off with my superelectrophile, my ethyl benzene, and it can initially form, it forms its carbocation intermediate. So one of them it forms is the meta one, right? I'll wiggle the hydrogen this time. I'm just showing one of the resonance forms of that. So that's going to be the rate determining step. Its transition state is going to look a lot like that carbocation, which is secondary. Another product that can form is the ortho and the para. So I'll draw the ortho one over here. The ortho one will have the ketone ortho, of course. And the carbocation can be secondary, tertiary. So that's why it's lower in energy. So its transition state is going to look more like it. So it's going to be a lower activation energy. It's going to be a faster reaction. And finally, here is your para. I think that's going to be a little bit lower in energy than the, oh crap. It's going to be a little bit, sorry. It's going to be a little bit lower in energy than the, I think, than this one because of steric hindrance. So we got resonance around the ring, secondary, tertiary, secondary, and its activation energy. It'll be similar, probably a little bit lower, right? A little lower transition state. And that's how you can explain that. Para's fastest, you get the most. Ortho's next fastest, you get the second most. Meta's the highest energy, it's the slowest. Get the least amount of that.